What's up, everybody? Welcome back to another live stream from Scalar Learning, where we are tackling ALEKS, the online curriculum, math curriculum, and we're tackling pre-algebra. So far, this is part 12 now out of this whole series. I'm just going to make sure we're working here and we're good. We are getting close to finishing the pi, and along with finishing the pi, that means I'm getting close to creating this video course that's going to be amazing for students that are studying pre-algebra, or even parents that want to freshen up on their skills. All you have to do is get ALEKS, a $20 monthly subscription, and then use my video course when it's done to step through and learn all the topics and learn everything there is to know about pre-algebra. 71% of the way done, and that's like you can see over there on the screen up here. That's 445 topics out of 630. Today I got a nice stretch. I can probably live stream for a solid 2 or 3 hours depending on my stamina, and we can hopefully knock out, well, we'll see what happens, but maybe knock out somewhere in the range of 30 or 50 topics today and get closer to that end goal of 630 topics. So without further ado, let's do it. All right, identifying rotational symmetry and angles of rotation. In each figure below, determine if it has rotational symmetry. So rotational symmetry is essentially where, oh, you know what? Sorry, 1 second. I'm missing something. All right. Sorry, my whiteboard, my Wacom tablet is missing its plug, so I can't draw. Let's get this set up here. See this, guys? So I gotta plug this back in. All right, cool. There we go. Okay, so let's see. Once again, identifying rotational symmetry and angles of rotation. All right, so for each figure below, determine if it has rotational symmetry. If it does, give the smallest angle of rotation needed for the figure to appear unmoved. So, rotational symmetry means that if we rotate an object, eventually, like if we rotate a certain amount of degrees, we'll get the same object once again. So for example, if we take a circle has perfect rotational symmetry. Any amount that you rotate it, it'll still be the exact same object. Now we can talk about a square. Square is probably a better example, more interesting example. Now I can rotate it by, let's say, to this point. I can kind of turn it and it becomes a diamond. But then if I rotate it again a little bit more, it will eventually come back to being a square. Therefore, a square has rotational symmetry. All right. So now let's look at this figure. If we think about this figure here, I'll just write it like this as a 4. As we rotate it, first we're rotating it, let's say 90 degrees. And then we'd rotate it down like this. None of these, we're not going to match up until it comes completely, oops, actually this would be over here, right? And then it would eventually go here, and then it would eventually go back. So you can see none of these rotations produce the same object as in the first drawing, like right here. It doesn't happen until it comes all the way back around. So I'd say there's no rotational symmetry here. Now, let's look at this one. I'd say yes, there is rotational symmetry, because we can see with the star, if we rotate it this much, right? If we kind of, let's say we got a star here, and we've got this one here. If I rotate it down to here, where now my star is, that point is down here, okay? We've got the same object. It's going to look the exact same. And that is, now, so we'd say, yes, it does have rotational symmetry. Now when we're talking about the angle, what's the angle? Well, think about it. We could rotate it once, twice, 3 times, 4 times, 5 times until we get back to the beginning. So 1/5 of those rotations, meaning 1/5 of 360, is going to give us that rotational symmetry angle, meaning how the least amount we have to turn it to have rotational symmetry to get the same object. So 1/5 of 360 is 72. All right, and there we go. Let's move on to the next one. Okay, so now we got this 5 here. If we look at the 5, right? The first time we turn it, it's definitely not the same. But when we turn it, so if we can kind of think about it like this. Here's this point, then I'm rotating it down by 90 degrees to that point, and then I rotate it down again. Right? We kind of rotate it down this way. And look, the original point now is down here, but look, it's the same. So I'd say this does have rotational symmetry, and we get to the same figure at 180 degrees when we flip it completely upside down. This one definitely has rotational symmetry, right? Because you can see that if you turn it down this far, it's going to be the same object. Well, how far is this? This is like 1/3 of going all the way around. 1/3 of 360, which is 120. Okay, next. This is interesting. Hopefully you can see that this probably doesn't have rotational symmetry, because obviously turning it 90 or 270 doesn't get us there. Even if you turn it all the way upside down, it would look like this, right? So it's not until it comes all the way around that it's the same. So we'd say no. This one definitely yes. And all we have to do is turn this guy here, this triangle, all the way to here. So how far is that? Well, we have to see how many of these spikes there are. There's 1, 2, 3, 4, 5, 6, 7, 8. That means we do 360 divided by 8, which is 45, I think. Yep, 45. All right, excellent. All right, next topic. Tony rented a truck for 1 day. There was a base fee of $16. Oh, wait. Solving a decimal word problem using a linear equation of the form ax plus b equals c. Tony rented a truck for 1 day. There was a base fee of $16.95, and there was an additional charge of 94 cents for each mile driven. So $16.95 plus the charge of 94 cents, 0.94 per mile, meaning multiplied by each mile. Right? 1 mile, 94 cents. 2 miles, $1.88, etc. Tony had to pay 149 cents when he returned the truck. How many miles did he drive? So he paid, so this base price plus the mile price equals the total, and in this case they're saying the total is 140.09. How many miles m did he drive? Well, this is a single variable equation. We got to solve for m, so let's do it. And we can use a calculator, which is nice. So first I'm going to isolate m. I'm going to subtract 16.95 from both sides. Okay. I could probably do this without the calculator here. 1, 3, 2, 1. So now we have 123.14 equals 0.94 m. Then we're going to divide both sides by 94 cents. And let's see. We've got 123.14 divided by 0.94, and we get 131. So that's 100. So m equals 131. All right, awesome. Next. Lisa received a $70 gift card for a coffee store. She used it in buying some coffee that cost $7.58 per pound. Per pound, so 758 times the number of pounds, right? 1 pound is 758, 2 pounds is 15 and 16. After buying the coffee, she had $32.10 left. So she spends $70, or she has $70. She spends this amount, meaning that takes away from the 70, and then afterwards she has 32.10 left. So I'm turning this whole sentence into equation. How many pounds P of coffee did she buy? Let's solve for P. So I'm going to subtract 70 from both sides. And I've got negative 7.58 P equals, this becomes negative 3790. Okay, negative 3790. And now to solve for P, we divide both sides by negative 7.58. Okay. And we get P equals, let's see, let's do the division. 37.9 divided by 7.58 equals 5 pounds. Next, for his long distance phone service, Miguel pays $7 monthly fee. So each month pays $7 flat plus 7 cents. Make sure not to write 7, but put this in cents since this is in, dollars. 0.07 cents per minute, so 0.07 times each minute. Last month, Miguel's long distance bill was $16.52, meaning the base fee, the monthly fee plus the cents per minute totaled up to be $16.52. And how many minutes was he billed? What was M? So let's solve for M. Subtract 7 from both sides. We get 0.07 M equals $9.52. Divide both sides by 0.07. M equals $9.52 divided by 0.07. And that's 136. 136 minutes. All right, next. Solving a two-step linear inequality problem type 1. Okay, so we've got x over 4 plus 3 is greater than negative 1. All we're trying to do here is isolate x. That's what they mean by solve. Just isolate x. So how do we do that? Just like a regular equation, we're going to subtract 3 from both sides. X over 4 is greater than negative 4. Now we need to get rid of this 4. X is dividing by 4, so the opposite of that is multiply by 4. Multiply both sides by 4. That cancels that out. And we have x is greater than negative 4 times 4 is negative 16. Okay, next. We got negative 2 plus 6x is greater than or equal to 22. So let's solve for x or isolate x. We're going to add 2 to both sides. The reason why I'm adding 2 is because a positive 2 plus a negative 2 goes to 0. That's what we want. The other way to think about it is we could subtract negative 2 from both sides. That's the same as adding 2. That goes away. We got 6x is greater than or equal to 24. And we divide both sides by 6. And we get x is greater than or equal to 4. Okay, next. Negative 14 is less than x over 2 minus 8. All right, let's isolate x. So we're going to add 8 to both sides. Right? I'm always getting rid of this number first, the number that's farthest away from x first. So I got x over 2 is greater than negative 6. And then I'm going to multiply both sides by 2, right? Opposite, x is dividing by 2, so we'll multiply by 2. And we get x is greater than negative 12. And there we go. Now you notice, see, this time x is on the right side. That's okay. I'm still reading it from the perspective of x. X is greater than negative 12. And we can definitely put it that way. Oh, whoops. I did it backwards. X is greater than negative 12. Okay, graphing a line given this equation in slope-intercept form, integer slope. Okay, y equals 3x minus 7. So we want to graph this, And the way we do it when we've got slope-intercept form, the way we graph a line is we look at these two values. Now, slope-intercept form is y equals mx plus b, where the m is my slope, b is my y-intercept, okay? So now, if we've got, we always start with the y-intercept. My y-intercept here is this value. It's not just 7, it's -7. So I'm going to start by saying, okay, well, my y-intercept means the place which it hits the y-axis, intercepts the y-axis, and it does that at -7. There's my first point. Now I look at the slope. The slope in this case is 3. 3 is not just the slope, it's actually that written as a fraction, which is 3 over 1. The top number is the rise, the bottom number is the run. So we start from our y-intercept value, and we say a rise of 3, meaning go up by 3, 1, 2, 3, and a run of 1, meaning we go to the right by 1. Boom, there's our second point. Now we have our 2 points. Connect the dots. And there you go. Okay, next. We've got y equals -x minus 2. So look now, my y-intercept is -2, okay, right here. And my slope is actually -1, okay? Which we can again say -1 over 1. So let's start with my y-intercept of -2. Boom. But now this is interesting because it's negative. So does that negative apply to both the top and bottom? No. Does it apply to the top or the bottom? Does it matter? No. You could just have to apply it to 1, because -1 over +1 is -1. +1 over -1 is also -1. So just assign it to one of them. It doesn't matter which. Now let's apply the rise and the run. So the rise is -1, meaning we go down 1. The run is +1, meaning we go right 1. And the reason why it doesn't matter where you apply it is if we had written it like this, 1 over -1, to go to the next term, I'd say a rise of +1 and a run of -1, and my point would be here. But that's the same line. You see, so it doesn't matter. We're still creating the same line. So it's irrelevant. And that's your line right there, and we are done. Okay. All right, last but not least, -5x plus 8. All right, so my y-intercept is 8. Now we got our slope of -5, or -5 over 1. So let's apply that slope. We're going to go down 5, 1, 2, 3, 4, 5, and to the right by 1. There's my second point. Connect the dots. And that's it. All right, Pythagorean Theorem. What is Pythagorean Theorem? Pythagorean Theorem says that for any right triangle, okay, a right triangle is just a triangle with a right angle. It's indicated by this. And a right angle is just 90 degrees. For any right triangle, if I call one of the legs A, the other leg B, and the hypotenuse C, hypotenuse is always C, then there's a relationship between the side lengths, which is A squared plus B squared equals C squared. And this is true for every right triangle. It's a beautiful theorem. So now let's look at this triangle here. And we've got x, 10, and 18. So by this logic, we can say that x squared plus 10 squared equals 18 squared. Okay, so now what we got to do is solve for x. So x squared is just x squared. 10 squared is 100. 18 squared is, I want to say 324, but I can't remember if that's correct. So let's double check because we got a calculator. Yeah, it's 324. Now let's solve for x. We subtract 100 from both sides. And we got x squared equals 224. So x squared is 224, but that's not x. How do we solve for x? Well, just like whenever we're isolating a variable, we always want to look at what's with the variable and do the opposite to finally get it down to x equals something. Well, the x is being squared. So what's the opposite of squaring? Square root. So I'm going to actually take the square root of both sides. I'm going to get x on the left side. And on the right side, we're going to have to calculate, and I believe this is not a rational, it's an irrational number, meaning it'll kind of go on forever. And there it is, 14 point whatever. But it says round to the nearest hundredth, so that becomes 14.9, and then we round that hundredth up to 7. 14.97. All right, next. Okay, now we got a different triangle. This is a little more interesting. I'll redraw it. So we got 10, 12, and x. But notice this time the x is the hypotenuse. How do I know that? Well, yeah, it's this diagonal side, but it's the side that's opposite the right angle. It's also the longest side. So now we know that 10 squared plus 12 squared equals x squared. Okay. So now let's evaluate it. 10 squared is 100. 12 squared is 144 equals x squared. 100 plus this is 244. And once again, we need to solve for x squared, so we take the square root of both sides. And x equals 15.62. Rounded to the nearest hundredth. All right, last but not least, notice where that right angle is this time. I didn't draw it perfectly, but here's my right angle this time, which means x is again opposite that. It's the hypotenuse. And it doesn't matter whether I put 8 or 9 first, right? It makes no difference. Just choosing one randomly, but it's a squared plus b squared or whatever. And then equals x squared. It becomes 64 plus 81 equals x squared. Okay, right? This is 145. Very close to 12, right? 144 is 12 squared. Let me make sure I did the math right. 81 and 64. Yeah. And then x equals square root of 145. 12.04. All right, next. Word problem on unit rates associated with ratios of fractions. Kareem gave 4 people candy. He split 3/4 of a pound among them. So he's splitting up 3/4 of a pound of candy among 4 people. So what is the unit rate in pounds per person? Well, it's 3/4 per 4, meaning, oops, that should be divided by 4. Okay, whenever we have something per something, it means the first quantity divided by the second quantity. So we're saying pounds per person, so divided by the number of persons, so it's 4/1. It's a fraction division, so we use keep, change, flip. So we say 3/4, change it to multiply, and flip that to 1/4. Multiply across, and we get 3/16 pounds per person. All right, next. The construction crew built 1/2 miles of road in 1/4 days. What is the unit rate in miles per day? So once again, it's miles per day. Okay, so we do this fraction division, keep, change, flip. We've got 1/2 times, change that to times, and flip that to 4/1. Cross simplify, of course, and that becomes 2/1 or 2. Okay, and problem number 3. She fills an aquarium to a depth of 250 meters in 6 minutes. What is the unit rate in minutes per meter? That means minutes per meter. right? Anything that comes after the per is what we're dividing by. So it's 6, I'm going to turn it into a fraction, over 1 divided by 2/5. Now let's do keep, change, flip. 6 over 1 times 5 over 2. Cross simplify, 1 and 3. Multiply across, and we get 15 over 1, which is 15. All right, solving a linear equation with several occurrences of the variables on both sides. Let's go. 6w minus 1 equals negative 7 times w plus 2. Simplify as much as possible. First thing, I always see these parentheses. I want to get rid of those by distributing. That's going to help us unlock that w and be able to combine the variables. So we have 6w minus 1 equals negative 7 times w, negative 7w, plus negative 7 times 2, which is negative 14. Okay, now we consolidate, meaning I'm going to bring the variables together by adding 7w to both sides, and we have 13w minus 1 equals negative 14. Okay, I'm going to move this 1 over, so I'm going to do the opposite of subtract, which is add 1 to both sides. Now I have 13w equals, that becomes negative 13, right? Negative 14 plus 1. And then last but not least, let's divide both sides by 13. And we get w equals negative 1. Okay, next. Negative 3 times u plus 9 equals negative 6u minus 21. Okay, let's first go ahead and start by distributing. We got negative 3u minus 27 equals negative 6u minus 21. Okay, let's bring the variables together first. So I got a negative 6u, so I'm going to add 6u to that, because adding a 6u to a negative 6u knocks it out, makes it go to 0. Add it to that side too. And 6u plus negative 3u is 3u. Right, it's like 6 minus 3. Add 27 to both sides. Get rid of this, and we got 3u equals 6. And then divide both sides by 3. And we've got u equals 2. All right, next we got 9v minus 26 equals 7 times v minus 6. All right, same thing. Get rid of these parentheses first by distributing, of course. We got 7v minus 42 equals 9v minus 26. I'm going to subtract 7v from both sides. And we've got 2v minus 26 equals negative 42. Then I'm going to add 26 to both sides. Get rid of that, and we got 2v equals negative 16, right? Negative 42 plus 26. It's like 42 minus 26. The answer is negative, and then divide by 2, and I got v equals negative 8. All right. Okay, using numerical methods to approximate a square root to the nearest tenth. Here we go. Okay, so use the calculator below to approximate 124 as a decimal to the tenth place. Without using the square root button. What? Oh, wow. Okay. That's interesting. Well, let's think about it like this. I know that 11 squared is 121. So we'll start there, right? 11 squared is 121. That's close to 124. So now let's start experimenting with different tenth values. Times 11.1 times 11.1. Oops. Oh shoot. 11.1 times 11.1. That's 123.1. Now let's try 11.2 times 11.2. This is in between here somewhere. Okay. as a decimal to the 10th place. So which one's closer? This is only 0.79 away. This one is 1.44 away. So I'm going to say it's 11.1. It's pretty close. All right, next. All right, 41. So what's my baseline? I'm trying to think of the perfect square that's closest to 41. On either side, we've got 36 and 49. But in terms of 41, this is closer. It's only 5 away. So I know it's going to be 6 point something. I also know, since it's kind of in the middle, it's probably going to be around like 6.5, maybe 6.4, something like that. I'd say 6.4 is my guess. So let's start there. 6.4 times 6.4. 40.96. Look, that's really close. That's probably the right answer, but let's just try 6.5 times 6.5. 42. That's 1.2. This one is almost perfect. So let's hit that. Okay. Next, square root of 118. So let's think perfect squares on either side is probably 100, 10 squared, and 121, 11 squared. This is so close. So it's going to be really close to 11, but it's not 11 point something because 11 is already past this. So it's like going to be close to 11. So it's probably going to be 10.9. I'm assuming this is going to be 10.9 is good. Let's try 10.9. Look at that. So close. Let's just try 10.8 just for fun. So, right, this is a much further away, so I'm going to say 10.9. Boom. Writing a rule to describe a translation. Triangle XYZ is translated 6 units down and 8 units, 6 units to the left and 8 units down. The result is that guy. Okay. The arrows below show that the coordinates on the left are mapped to the coordinates on the right. Fill in the blanks to give the coordinates after the translation. Okay, so X is 1, 1. So think about it. What we're doing is we're translating to the left by 6 units, so I'm subtracting 6 from this guy. And down by 8 units. Down is, again, affecting the Y, so I'm subtracting 8 there. So if we look at 1, 1, it's going to go to -5, in which we can see makes sense. And then subtracting that 8, it becomes -7. Right? Same thing, 2, 4, the new Y becomes, if we're subtracting 6, it becomes -4. Subtracting 8 becomes -4. And we can probably see that right here, -4 and -4 for Y. And then last but not least, Z, I'm again subtracting -6 from, or subtracting 6 from the 6, which is 0. And then I'm subtracting 8 from the 2, which is -6. And we can see Z is 0, -6. And this is it right here. I don't know why they give so many options. It's like, yeah, -6 and -8. That's what we did right there. A lot of different options, but that should be it. All right, next. So now we've got ABC is translated 7 units to the right. That's positive change on the X, so we're adding 7 there, and 5 units up, we're adding 5 right there. For the rule, I can already tell you that it's going to be X plus 7, Y plus 5, right? So we're definitely talking about this one. But now let's go to the translation. And like we can actually plot out the points if you want up here, but I kind of like just applying the rules. So -4 plus 7 is 3. -5 plus 5 is 0. -7 plus 7 is 0. -4 plus 5 is 1. -8 plus 7 is -1. -1 plus 5 is 4. And we can verify this really quickly. So A is 3, 0, like we said. B is 0, 1, like we said, and that's negative 1, 4. C is negative 1, 4. Let's change this to x and y here. So x is translated 5 units to the right. So again, we're adding 5, and 8 units down, we're subtracting 8. So let's put in that rule first. We're adding 5 to the x, subtracting 8 from the y, so it's right there. Okay, so let's just do the x's real quick. Negative 7 plus 5 is negative 2. Negative 8 plus 5 is negative 3. Negative 4 plus 5 is 1. And now let's subtract 8 from all these. 5 minus 8 is negative 3. 8 minus 8 is 0. 4 minus 8 is negative 4. All right, we're just doing a quick log out to get the speed back up. Here we go. Okay, finding angle measures of a triangle given two angles of a similar triangle. Now, similar triangles, let's talk about this, because similar triangles are basically two triangles that sort of like one, they look almost identical. They look like, one looks like a miniature version of the other. Okay, but there's an interesting relationship between similar triangles. Yes, the sides are proportionate, but the angles for similar triangles are all equal. Okay, so these two angles are equal, these two are equal, these two are equal. All right, now that's very important, because if we know these values of, if we know the values of a similar triangle, of one triangle and another one similar, we thereby know the angles of the similar triangle. So now let's use this image here that they gave us. I'm going to put it over here so we can write on it. Okay, so we need to find C, D, and E. Okay, and their triangles are similar. So the way I'm looking at it is, this is similar to this, or that matches up with that. That matches up with that. Not that they're equal, okay, but I'm just showing they're proportionate. The reason why that matters is because that helps us line up the angle. Since this and this line up with this and this, the angle in between, E, is the same as x, which means that if x is 80, E is 80. If W is 40, D is 40. And then by the rule that all the angles add up to 180 degrees, if this is 80, this is 40, that's 120, this one has to be 60 degrees. So C is 60, D is 40, and E is 80. All right. All right, here we go. So this is 15. Now I'm going to match up. A looks like it matches up with R, so I'm going to say that R here is 15 degrees, right? C is probably this guy Q, which is 40. And then P is this guy here. We don't have an angle, so let's use our rule. 15 plus 40 is 55. And since 55 plus that last one is 80, I'm going to subtract it from 80. That means this big angle here is 125 degrees, okay? So now let's fill this out. P is 125, Q is 40, and R is 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. All right, the two triangles below are similar. Also, same deal here. Okay, next 65, 90, and E. So now we got to find these angles. So again, G looks like it matches up with K. So I'm going to say this is 65. This is 90. So this guy, L is 90, right angle. And then J, well, 90 plus 65 is 155. So 155 plus what equals 180? 25. So this one is 25. J is 25. K is 65. L is 90. Finding the radius or the diameter of a circle given its circumference. So I'm going to draw out a circle here. So the circumference of a circular painting is 59.66. That's the circumference. What is the radius of the painting? All right, so we're trying to solve for radius. Now, first of all, to solve for radius, we need to know the formula for circumference. The formula for circumference is 2 pi r equals circumference. So in this case, 2 pi r equals 59.66. And they want us to use 3.14 for pi. Guess what? Now we just solve for radius. First, I'm going to multiply 2 times that, so I get 6.28 r equals 59.66. Divide both sides by 6.28. 6.28. Okay. And we have 59.66 divided by 6.28. 9.5. So the radius is 9.5. Okay, next. The circumference of a circular field is 279.46. What is the diameter? So we can use that same equation. By the way, circumference is 2 pi r. It's also diameter times pi, because 2 times the radius is diameter. So let's use that formula this time. So diameter times pi, but they want us to use 3.14 for pi. This is a nice, simple one to solve. We just divide both sides by 3.14. So we have 279.46 divided by 3.14. 89. All right, next, the circumference of a circular garden is 150.72 feet. 150.72 equals 2 pi r. And then what is the radius? So again, for pi, we're using 3.14. And we're going to solve for r. So 3.14 times 2, 6.28 times radius. Divide both sides by 6.28. 150.72 divided by 6.28 equals 24. Volume of a triangular prism. Anytime we're talking about a prism, okay, we're talking about a singular shape that's like extended back by straight lines. So let me kind of show you why that's important. So we've got this shape, which is in this case a triangle, that is then extended backwards. So the way I think about it for any prism is all we have to do is identify that shape which is being extended. In this case, this is this triangle. Calculate the area of this triangle. and then multiply it by whatever this length is that it's being extended by. In this case, it's 9. So how do we calculate the area of this triangle? Well, area is 1/2 base times height. Looks like the height is 5, and it looks like the base is 8. So 1/2 times base times height. So that, and then that whole thing times this part. 1/2 base times height times, we could say length, or whatever this value is, 9. So 1/2 times 8 is 4. 4 times 5 is 20. So 20 times 9, which is 180. And since it's volume, we're talking about cubic meters. Next. Same thing, I'm identifying the figure, the shape that's being extended, and it's this triangle here. What's the area of this triangle? It's again 1/2 base times height. Looks the same. 1/2 base times height. And then that is multiplied by this value that is extending it, which is the 8. So this whole thing times 8. So 1/2 times 5 times 8. 5 times 8 is 40. 1/2 of that is 20. Times 8 is 160. Okay. Same deal. We've got this triangle that's being extended back. So 1/2 base times height, and then times 7, times that value there. So 1/2 of 25 times 7. 1/2 of 25 is 12.5 times 7. 7 times that is 84. Plus 3.5 is 87.5, right? Okay, next. Sorry, 1 second. All right. Just taking a stretch break here. Okay. Using box and whisker plots to compare data sets. So I'm going to have to explain what a box and whisker plot is first. Okay, so we got a box and whisker plot, and what it essentially means. Okay, so here it's saying it summarizes the test scores for each class. So we got 2 classes, class A and class B. So let me identify all these different pieces. This center line right here for both of these is the median. The ends of this box are the 25th percentile and the 75th percentile, meaning at this point, everything to the left is in the bottom 25th percentile. Everything to the right is in the upper 25th percentile. And then this is the max score, the highest that anybody got. This is the min score. So that's what a box and whisker plot tells you. Those are all the pieces of information. So now it's really nice because we can answer these questions pretty easily. Which class had the highest score? Well, which one had the one farthest to the right? This guy, class B. This person got an 89%. Which class had the highest test score with the larger interquartile range? Interquartile range is this range right here between the 25th and 75th percentile. So which one had a larger one? Well, it looks like this goes from 70 to 78, so this is an interquartile range of 8. This one goes from 60 to 68, so they're both 8. So I'm going to say they're equal. A score above 70 is considered passing. Which class had more passing scores? Where's 70? So in this case, it looks here for class A, we had, since this is the 25th percentile cutoff, it looks like 75% of the class got a 70 or higher. Here, it looks like less than 75% passed. So I'm saying class A did a lot better. Whoops, class A. Which class had a higher median test score? Median is this line right here and this line right here. Clearly this one is higher, so class A. Okay, here we go. This looks like athletes for a cycling race, and this is the distance in miles that they traveled. Okay, which athlete had distances with a larger, two athletes. Which athlete had distances with a larger interquartile range? Clearly athlete B, right? This range is bigger here. Which athlete went on the shortest training ride? Meaning which had the lowest value, and it's clearly B, right? They went on a ride of 17 miles. Which athlete had a smaller range of distances, meaning distance from here to here, or sorry, here to here, and it's clearly athlete A. Which athlete had a greater median? That's this line again, here and here, and it's B. Okay, this is temperatures in Fahrenheit. We got 2 cities. Let's do it. Which city had noon temperatures with a larger interquartile range? This guy, right? This is from here to here is bigger than from here to here. So B. Which city had a larger median? It's this guy, right? The median's higher there for city A. Which city had the highest noon temperature? Right here. High temperature of like 88. City A. And then which city had more noon temperatures above 77? So here's 77. Okay. So this is a little bit trickier because it's like in the interquartile range for both. My assumption is because it's higher up here in terms of like, I mean, sorry, it's the same amount, but this is like a higher fraction of the interquartile range. I'm going to say that city A probably had more temperatures above 77. Not because of this extension, but because like if we look at this pocket, this represents 50%, right? 25 to 75. This represents 25 to 75 too. So this is like a smaller fraction of that amount, which is why A should be correct. Oh, it's not. Okay, let's see which one of the answers is incorrect. Which city had more noon temperatures above 77? Oh, 77. I put 73. Sorry. So 77 is right here. Oh, it's equal. Because this is the 75th percentile. Ah, I missed that. There we go. Little mistake. Let's do one more. Okay. Oops. All right, this is number of students took a final exam in 2 classes. Which class had a smaller range of test scores? This class, right? It's only from here to here. So that's A. Which class had test scores with a larger interquartile range? That's from here to here. It's bigger. So class B. Which class had a higher median score? A, right? That's a median of 80. This is a median of 73. Which class had the highest test score? Right here, class B. A score of 88. All right, next, finding the slope. see. Finding slope given the graph of a line on a grid. Okay. So we're trying to find the slope, and if there's a couple different ways we can do this. We can look at these two coordinates and we can chart the trajectory to go from here to here. We can also take these coordinates and find the slope that way from 2 points. But the easiest thing to do is look at these 2 points that I highlighted and be like, okay, to go from here to here, what do? We go down by 2 and we go to the right by 3. And slope is always rise over run. So we're going down by 2, meaning a rise of -2, and we're going to the right by 3, a +3. And therefore the slope is -2/3. All right, next. Now we have a same idea here. Let me erase this. So we have let's go from here to here. So we go down by 1, 2, 3, 4, 5, and then to the right by 2. So slope of -5 over +2. And we can usually leave this in improper fraction. That makes the most sense in terms of representing slope, -5 over 2. Okay, next. Okay, and now we go from here to here. We go up 2, right? Rise of +2. And then we go to the right 1, 2, 3, 4, 5, 6. Rise of +6. But we can reduce that to 1 over 3. So slope of 1/3. All right, very nice. Quotient rule with negative exponents, problem type 1. B to the -7 over B to the -6. And we want only positive exponents. Now, there's a couple ways to think about this. The first way to think about this is, again, when we have a fraction, or sorry, a fraction with something with an exponent on top, exponent on bottom, same base, we can just subtract down. So this is the same as B to the -7 minus -6. Again, this becomes a minus, negative becomes a plus, and we get B to the -1. So -7 plus 6 is -1. We want to represent this with a positive exponent, so that just becomes 1 over B to the 1. Right? Because anytime we have a negative exponent, we just put a 1 over it, and then the exponent becomes positive. That's one way. The other way to think about this is when we have a negative exponent, we just flip it up to the top. So this becomes actually B to the 6, and this -7 comes down here to the denominator, becomes B over 7. Right? You see how this works? And then now we have two positive exponents, and it's kind of like now we can subtract, but it's like it doesn't matter which way to go. We don't have to subtract down. I mean, we can, but we can also just be like, okay, well, 7 minus 6, this guy cancels out to 1, and we just have 1b left in the bottom, 1 over b. 1 over b or 1 over b to the first, same thing. Okay, next. X to the -6 over x to the -2. So let's flip these guys, and we get x squared over x to the 6th. Okay. And then now we're going to subtract up, kind of, right? So 6 minus 2 is 4. This one's completely gone, so we have 1 over x to the 4th. And there we go. All right, here we go. Last one, we've got b to the 6th over b to the -2. Now, we can bring this up, right? And then the denominator is essentially gone. So it's then b squared times, this is going to be multiplying this guy, b to the 6th. And then this is our basic addition exponent rule. B squared times b to the 6th becomes b to the 8th. We add those together, and we're done. Next. So now we're talking about square roots. Now this gets into something called imaginary numbers. Here's the deal. Square roots of perfect squares with signs. You cannot take a real square root of a negative number. Well, you can, but you get what's called an imaginary number, which is not a real number. So the reason why is because the square root is when you're trying to find a number that times itself equals a number. So for example, square root of 4 is 2, right? Because 2 times 2 times itself equals 4. Square root of 16 is 4. But why can't we take a square root of a negative number, of like negative 16? Because there's no number 4 that when multiplied against itself gives you negative 16. Like 4 times 4 gives you positive 16. Negative 4 times negative 4 also gives you positive 16. No real number times itself gives you a negative. But so that's when we say it's not a real number. So look right here. I know I have a negative in front of this, but the fact that I'm trying to take a square root of a negative number, we can right off the bat say not a real number. What about this guy? This is okay because the negative is not on the 121, it's on the outside. So we evaluate, we take the square root of 121, which is 11, and then stick the negative on there, and our answer is negative 11. Okay, next. We've got square root of negative square root of 1. Well, square root of 1 is just 1. Put that negative on to the end of it, it's just negative 1. What about this? We're taking square root of a negative number, not real. Same thing, square root of a negative, not real. Square root of 100 is 10, the negative on top, negative 10. There we go. So let's now do the next one. All right, the effect of dilation on side length. In the figure, do a dilation centered at the origin with a scale factor of 3. Then answer each part. Okay, so scale factor of 3 means boop, boop, boop. We just move it up to 3. And now let's answer. The longest side of the original figure. The original figure is 2, that side down there. The longest side length of the final figure. Well, since it's a scale factor of 3, it should be 3 times 2, which is 6. Let's verify that. 1, 2, 3, 4, 5, 6. Cool. Fill in the blank to make a true statement. Longest side length of the final figure equals 3 times the longest side length of the original figure, right? We're just multiplying by the scale factor. A dilation with a positive scale factor greater than 1 gives a final figure larger. Yes, that's true because that's what we have here. The original figure and the final figure are similar. Yes, when we dilate something, we're making a similar figure, which means the angles are all equal and the side lengths are all proportionate. Okay, next. We want a scale factor of 1/4. So this is, 3/4, 2/4, and 1/4. It's like 0.25, 1/4. Shortest side length of the original figure is this guy, 1, 2, 3, 4. Now it's the same thing, right? It's like multiplying that scale factor times that gives us the final figure, which is 1, and we can see it is also 1. Shortest side length of the final figure equals 1/4 times shortest side length of the original figure. A dilation with a positive scale factor less than 1 gives a final figure smaller. Yes. The original figure and the final figure are not similar. That's false. They are similar, right? You can see that the angles are all the same. They look the same, just one is miniature. Okay, we want a scale factor of 2, which means we're effectively doubling the size of this guy. Shortest side length of the original figure looks like 1, 2. So of course, since we're doubling, it's going to go to 4 for the new one, but we can verify 1, 2, 3, 4, yes. Shortest side length of the final figure equals 2 times the original. Dilation with the positive scale factor greater than 1 gives a figure smaller, false. We have a bigger one. The original figure and the final figure are not similar, false. Surface area of a cube or a rectangular prism. Be sure to include the correct unit in your answer. So how do we find surface area? Think about it like this. A cube has how many faces? It's like a dice. It has 6 sides. So what we got to do is find the area of one face of one of these sides and then multiply it by 6. So since this is 3 by 3, this is an area of 9. So 9 and 6 of those sides, so 9 times 6 is 54. And since we're talking about area, it's always squared, feet squared. Next. So now this is a little different because it's a cube. It's not a cube, meaning not all the faces are equal. We got a rectangular prism. So we've got unique sides. So it's like we got 9, we got 7, and we got 3. We've got 3 unique faces because this front face is the same as whatever we got in the back, right? It's the same as that one. So it's kind of like we find these 3 unique areas, add them up, and then double them, and we get our total surface area. So the surface area of this side, 7 times 9, which is 63. This one is 3 times 7, right? Because these lengths are 7. 3 times 7 is 21. And the top is 3 by 9, right? Because this is 3, this is 9, is 27. So now we add those up. 11. So 111 times 2 is 222. And now we got a nice cube. So the cubes are the easiest because it's just one face times 6. So since it's 5 by 5, we've got an area of 25. 25 times 6, 150. Constructing a Venn diagram to classify rational numbers. All right. Build a Venn diagram. So what is a Venn diagram? A Venn diagram, it kind of shows different universes, okay? I'm going to explain more as I kind of create this. So if this can't move. Yeah, this can't move. Okay. So these are 3 universes. We got this big box, we got a second universe, and we got a third universe. Notice this third universe is part of the other 2 universes. It's inside of both of them. And that's how we want to think about it. So in terms of whole numbers, rational, integers, the largest universe should be most inclusive. So what's the biggest group? It's rational numbers. Okay, so rational is going to be this gigantic one. Then within rational numbers, we have integers and whole numbers. They're both considered rational. But which one's bigger? Well, whole numbers are like 1, 2, 3, 4, 0, etc. But it's only positive. Integers are all these plus the negatives. So look, integers is a larger group. So I'm going to put integers here. And then whole numbers are like, it's all the positives and 0 of integers. So we're cool there. Now let's look at where we place these. First, let's start with anything that's a whole number. So I told you that a whole number is basically 0 and positives. So that's 0. There's no other positives, and there's no other whole numbers. So that's it. What about these guys? -4. That's an integer because it's a whole number, but it's negative, so that falls in the integer category. The rest of these are all rational, so they kind of come out here, here, and here. You can see they're not integers. They're not whole numbers, and that's where they go. And this is how you make a Venn diagram. Let's do the next one. Same deal. Rationals, integers, whole numbers. Here we got a nice whole number. Yes, it's also an integer, but we want the most specific category, which is a whole number. This is also a whole number. These guys are integers. And these are neither, so these are just rational numbers. -12 is a nice whole number. 28 is a nice whole number. -42 is an integer. And then these guys are non-whole numbers or integers, and they're rationals. multiplicative property of inequality with integers. We have y over -4 is greater than -2. All we're doing is we're isolating y. Y is dividing -4, so we got to do the opposite of that, which is multiply both sides by -4. When we do that, okay, same thing happens. -2 times -4 is 8. But anytime in an inequality we multiply or divide by a negative number, we have to flip the inequality. So it flips, and now we've got y is less than 8. Next, we got -2x is greater than 14. So I'm going to divide both sides by that -2. Again, since we're dividing by negative, I got to flip the inequality. X is less than -7. Oh, less than or equal to. I missed that sign. Boop, boop. So I got to watch those details. -15 is less than or equal to 5w. So I'm going to divide both sides by 5. Since we're not dividing by a negative, we're dividing by positive. This does not flip, and it stays like that. U over -2 is less than -8. So I'm going to multiply both sides by -2. You got to flip this because we're multiplying by negative. U is greater than 16. Domain and range from ordered pairs. S is defined as follows. Give the domain and range of S. Write your answers using set notation. Domain is simply the X values, okay? It's where all the X values are. So in this case, my domain is 2, 3, 2, right? Because those are all the X values. My range is all the Y values, which is A, D, and C. A, D, and C. And set notation, we gotta, oops, I should have done it like this. It's not gonna let me do it now. So we do 2, 3, 2. Oh, we don't have to write 2 again, actually. That's fine. Oh. And then this guy, it's gonna be A, D, C. Okay, next. So remember domain X, range Y. So my domain is -1, 8, and -5. And my range is the Y is 7, 7 again, we don't need to write that, and 0. Okay, domain is, let's see here, we got 5, 0, and 9. There's a second 9, but we don't need to repeat that. And then here we got for the range, we got M, 5, N, and P. Identifying proportional relationships in graphs, advanced. Each graph below shows a relationship between X and Y. All right, let's start. For each graph, determine whether x and y are proportional. Okay. So first of all, when we're talking about proportional relationships, one of the most important thing, the first thing you have to identify is, does this graph hit the origin? Does it go through 0? If it doesn't, like in this one, right off the bat, it's not proportional. Okay, then once we identify that, we can kind of look and say that then this is definitely proportionate. And it goes through the origin, and we can see that if I take my x value, which is 4, to get my y value, I multiply it by 1/4. Same thing here. I got an 8 value to get 2, I multiply it by 1/4. So y is 1/4 times x. You'll notice the other way to solve that is it's the slope. My slope is up 1 over 4, up 1 over 4. That's 1 over 4. This is also a proportionate relationship. And what's the slope? It's up 5 over 1. Also, we have x is 1, y is 5, x is 2, y is 10. Oh, shoot, that's supposed to be 5. I wrote that incorrectly. There we go. Okay, next. Is this proportional? No. Doesn't hit the origin, not linear, so no go. This is proportionate. Yes, this is not proportionate. It does not hit the origin. So here, what's the y is what times x? Well, let's look at the slope. Up 5 over 4. So it's going to be 5 over 4. And we can see that 5/4 of 4 is 5. 5/4 of 8 is 10. Not proportional, because it's not linear, doesn't hit the origin, does not hit the origin, does hit the origin. And so it's proportionate, and we can find y is what times x? It's the slope. Up 4 over 5. So 4/5, and we can test it out. 4/5 times 5, yes, that's 4. 4/5 times 10, yes, that's 8. All right, let's keep going. Introduction to the product rule with negative exponents, whole number base. Okay. So we have 9 to the negative 2 times 9 to the negative 6. Well, what are we doing with the product rule? Again, we got the same base. We're just adding the exponents. So negative 2 plus negative 6 is just negative 8, right? But then we want to rewrite using a single positive exponent. How do we convert this to a positive exponent? Remember, if it's a negative exponent, we just throw it under 1 and write it like that. So it's 1 over 9 to the 8th. Five to the 9th times 5 to the negative 3rd. Add these exponents and we get 5 to the 6th. And that's it. It's positive. Good to go. Eight squared times 8 to the negative 8. Add these guys. Negative 8 plus 2 is 8 to the negative 6th, but we want it to be a positive exponent, so I'm going to throw it over like this, 1 over 8 to the 6th. Next. Okay, let me take a quick stretch break. I'm going to log out, by the way, because you can see that the program is starting to slow down. Let's log out. All right. Let's pick it back up. Here we go. Here we go. Adding or subtracting numbers written in scientific notation. Same exponents, basic. Now, when we are doing this with scientific notation and we have the same exponents, it's pretty easy actually. Because all we're doing is we're subtracting 7.9 from 2.6 from 7.9. So all we got to do is say it's 7.9 minus 2.6. It's 5.3, which is our final answer is going to still be 5.3 times 10 to the 8th. Next, 2 plus 5, that's pretty basic, right? 2 plus 5 is just 7, and then times 10 to the 3rd. And next is 7 minus 5, which is 2 times 10 to the 9th. Multiplying numbers written in scientific notation, basic. So now it's a little more interesting. Same deal if they have the same base, or sorry, different bases. Wait, does it say oh yeah, okay. Now with multiplication, it's a little bit more interesting. We have 5 times 10 to the 3rd, and then times 7.5 times 10 to the 5th. So what I usually do is I kind of let these guys multiply together, because this is multiplying the whole thing. So it's kind of like I can combine this with this, and I can combine this with this. It's the way I like to do it. So 5 times 7.5, I can do that in my head. That's 35 plus 2.5, which is 37.5. And then 10 to the 3rd times 10 to the 5th, we just add the exponents, becomes 10 to the 8th. Now we're almost there, but remember in scientific notation, we don't want to have 2 numbers to the left. We only want to have 1 number to the left of the decimal. So I'm going to move the decimal 1 spot over. Since I'm making this number smaller, this number gets bigger by 1. So it becomes 3.75 times 10 to the 9th. Next, 2 times 10 squared, 2 times 10 to the 4th. So same deal. 2 and 2 multiplying give us 4. 10 squared times 10 to the 4th becomes 10 to the 6th. Next we got 1.3 times 10 squared times 3 times 10 to the 5th. So 1.3 times 3 is 3.9. 10 squared times 10 to the 5th is 10 to the 7th. Approximating the location of irrational numbers on a number line. Okay. So 0.84. Now square root of 84. We can use a calculator. Oops. Square root of 84 is 9.165. So this is 9.1, 9.2, 9.3, etc. This looks like it's right in between 9.1 and 9.2. So let's try our best. 9.165. Oops. Let's see if we can do it better than that. Okay, next. Square root of 53. 7.28. That's pretty close to 7.3. Right around here. All right, next, and square root of 71. 8.43. So 8.43. 1, 2, 3, 4, and then 4, 3. All right. Identifying side lengths that give right triangles. Okay. So a right triangle means that we're going to have to satisfy Pythagorean's theorem, which is a squared plus b squared equals c squared. And c is, again, the hypotenuse, which means it's the longest side. So in this case, this means that 20 squared plus 21 squared has to equal 29 squared. So we're going to use our calculator here. And first I'm going to calculate 29 squared, which is 841. And then I'm going to calculate 20 squared and 21 squared. 20 squared plus 21 squared equals 841. Right? So that means a squared plus b squared equals c squared. It's a right triangle. Next one, we have 13 squared plus 20 squared, and that equals 569. So a squared plus b squared is 569. And then what is 26 squared? That is 676. They are not equal, so it's not a right triangle. Next, we have 4, 8, and 9. So 4 squared is 16, plus 8 squared is 64, and that equals 80. 9 squared is 81. Not a right triangle. Last but not least, 6 squared plus 9 squared, 11 squared. Do these guys equal each other? Let's see. 6 squared is 36. 9 squared is 81. This is 121. And I can tell you this is 117. Does not equal 121. It's not a right triangle. Okay, next. All right, we have a 3, 4, 5. I know this is a right triangle because this is a Pythagorean triple. 9 plus 16, 3 squared plus 4 squared does equal 25 equals 5 squared, and that's good to go. 10, 26, 28. I have a feeling it is, but let's see. 10 squared plus 26 squared equals 776. 28 squared, ooh, 784. They're not a right triangle. 10, 12, 16. 10 squared plus 12 squared equals 244. 16 squared is 256. They're not equal, not a right triangle. And last, 21 squared plus 28 squared equals 1225. And let's see what 35 squared is. 1225, it's a right triangle. Last, 1, 7, 4, 24, 25. I think that's a Pythagorean triple, so I think it is, but let's try it. 7 squared plus 24 squared equals 625. 25 squared is 625, so that's good. Next, we have 6 squared plus 7 squared. Whoops, 6 squared plus 7 squared equals 85. 9 squared is 81, not a right triangle. 15 squared plus 35 squared equals 1450. 40 squared is definitely 1600, so not a right triangle. And then 15, 20, 25. 15 squared plus 20 squared equals 625. 25 squared is 625. It's a right triangle. Demonstrating the converse of the Pythagorean theorem. Compute the sum of the squares of the shorter lengths. So 5 squared plus 16 squared equals, that's 25 plus 256 is 281. 18 squared is 324. And since these aren't equal, we can see that it's not a right triangle, but I can also say that when c squared is larger than a squared plus b squared, it's what's called an obtuse triangle. And that's true. You can see it's an obtuse triangle, meaning it has one angle greater than 90 degrees right there. What about this? 7 squared plus 24 squared. I happen to know this is 625, but we can calculate it here. It's 7 squared plus 24 squared equals 625. 25 squared is 625. This is the Pythagorean theorem. A squared plus b squared does equal c squared, so it's a right triangle. All right, next, 8 squared plus 11 squared, that's 64 plus 121 is 185. Then we have 12 squared is 144. They're not equal. C squared is less than a squared plus b squared, which means it's acute. And it looks like acute, right? They're all less than 90 degrees. Okay, 6 squared plus 7 squared is 36 plus 42 is 78. This is 121. This is way larger than those two. Therefore, it's obtuse. Oops. 30. Oh, I messed up. 6 squared plus 49. Excuse me. 36 plus 49 is 85. Yeah. Next, 11 squared plus 12 squared, so that's 11. 11 squared plus 12 squared equals 265. 14 squared is 196. Since it's smaller, this is acute. 6 squared plus 8 squared is 100. 36 plus 64 is 100. 10 squared is 100. A squared plus b squared does equal c squared, therefore it's right. Okay, next. This is 49, so 7 squared is 49 plus 120, oops. Squared plus 121, 11 squared equals 170. This is 256. Since c squared is bigger than a squared plus b squared, we got an obtuse triangle. And then this is 25 plus 144, which is 169. 13 squared is also 169, and it's right. And we can see that it looks like a right triangle. Excellent. All right, next we got volume of a piecewise rectangular prism. Now, what we're going to do here is we're going to basically, with most of these piecewise functions, or piecewise figures, what we're doing is we're breaking it up into manageable pieces and then calculating the different areas individually and then adding them up. So for example, here, if I draw a line like this across here, now we got two nice rectangular prisms that are easier to calculate. So how do we do that? So we want the volume. So first of all, what's the volume of this solid right here? It's 6 by 2 by 6, right? Calculate the volume, you just do length times width times height. So 6 times 2 is 12 times 6 is a volume of 72. What about this one? 2 by 3 by 7. 2 times 3 is 6 times 7 is 42. Then we add these two values and we get 114 yards cubed. Next. Okay, now we're going to take the volume of this guy and let me put it up here, and then we will put a little line through it. Same deal. We're going to cut through here. Now, let's calculate the volume. We've got 4 by 4 by 5, right? So 4 times, let's do 5 times 4 first, which is 20, times 4, which is 80. So this is 80 feet cubed. What about this one? 5 times 5 times 3. 5 times 5 is 25, times 3 is 75. 75 plus 80 is 155 feet cubed. Okay, next. Okay, here we go. Now I'm going to cut it across here. And now we've got 3 by 8 by 7. So 3 times 7 is 21. I'm just doing what's easier first. 21 times 8 is 168. And then we got 5 times 4 times 8. 5 times 4 is 20. Times 8 is 160. Add that up and we get 328. All right, there we go. Excellent. Let's keep rolling. Word problem involving multiplication or division with mixed numbers. So Linda used a total of 5 1/6 gallons of gas while driving her car. Each hour she was driving, she used 5 9 gallons of gas. What was the total number of hours she was driving? Okay, so check it out. She uses 5 9 per hour, meaning 5 9 times each hour. And it gives us the total amount of gas, which in this case, the total gas is 5 1/6. So we need to solve for h. So if I'm multiplying h by 5 9, I got to multiply by the reciprocal, multiply both sides by the reciprocal, which is 9/5. That cancels out. Now, how do I multiply these two fractions? First, I got to turn this into an improper fraction. Anytime we do division or multiplication of fractions, we can't be messing with mixed numbers. So multiply the denominator and add to the numerator. So it's 30 plus 1, which is 31 over 6. Times 9 over 5, and let's cross simplify. Divide these by 3, and that's 3 and 2, and then multiply across. And we get 93 over 10. And then this reduces in the way we can divide by 10. It goes in 9 times, so that's 9 wholes, and a remainder of 3/10. So it's 9 3/10. That's how many hours. 9 3/10. Okay, next, we got a farmer's land is separated into sections of size 3 1/5 acres. Suppose there are 2 3/8 such sections. So he's got these plots that are that big, and he's got 2 3/8 of them. How many does the farmer own? Well, that's just multiplication, right? If he had 5-acre plots and he had 3 of them, you just multiply 3 times 5. So we do the same here. 3 1/5 times 2 3/8, same thing. Turn them into improper fractions. 3 times 5 is 15, plus 1 is 16 over 5, times 2 times 8 is 16, plus 3 is 19 over 8. And then let's cross simplify, divide these by 8, we get 1 and 2. Multiply across, and we get 38 over 5. 5 goes into 38 7 times with a remainder of 3. So it's 7 3/5 acres. Okay, next. We've got sugar fills 10 containers. If each container holds 3 1/6 tons of sugar, all right, what is the amount of sugar in the entire shipment? So we've got 10 containers where each container is that, so it's multiplication. 10 over 1 times 3 1/6. Same thing, let's turn this into an improper fraction. So it's 10 over 1 times 18 plus 1 is 19 over 6. Cross simplify, divide by 2, we get 3 and 5. 5 times 9 is 50, plus 45 is 95 over 3. And now we can say, well, 95, let's divide by 3, and that's 31. And we'll do the division here. It's 3, 9, subtract, bring down to 5, 1, 3, and we have a remainder of 2. So it's 31 with a remainder of 2 over 3, so 31 2/3 tons. All right, that's it. Let me take a quick stretch break. 1 second. Drinking some coffee. Let's see here. Woo! All right. I'm going to check over here real quick just to see if we have any comments going. Just want to stop and say that you were super helpful and raise my SAT score with these videos. Hey, what's up, villain? So my SAT practice problems. So first of all, Joshua, if you're still watching, thank you so much. I'm so happy that you were able to raise your scores and that my videos were helpful. That's like the greatest thing for me to hear. It really makes me feel good. That's why I do what I do. For the villain, for SAT practice problems, I usually do those on Wednesday. So tomorrow I will be doing a set of 5 problems. But the good news is next week when we're kind of gearing up for the next SAT. I'm going to be doing a live stream every day, Monday through Friday, to get you ready for the SAT. I'm probably going to do longer sections, like calculator section, full non-calculator section, just one every day. So that should be really huge. So make sure to check in for that the following week if you're taking the SAT in August. All right, cool. Thanks, man. All right, so I'm going to jump back into the ALEKS Pi and rock out these pre-algebra problems. Let me log out and log back in. It's slowing down again. So we're at about an hour and 40 minutes. Okay, we're at 75%. That's exciting. Let's keep going. Let's see how long we can keep up the energy. Okay. Here we go. Identifying proportional relationships in tables by calculating unit rates, fractions. For each table, determine whether it shows that x and y are proportional. If x and y are proportional, fill in the blank with a number in simplest form. If we're talking about proportional, what we should see is we should see as one increases by a certain amount, the other one increases by an equivalent amount. So it's like, let's see here. If I'm going to look at this, it's almost like calculating a slope, right? So I can do like 21 minus 12, which is 9, and then 35 minus 20, which is 15, which we can reduce that slope, right? So it's 9 over 15, which is 3 over 5. So every time this one changes by 3, this one should change by 5. Okay, and I can see a similar slope here. It's changing by 6, which means this should change by 10. It does. Changes by 3, changes by 5. So this looks like it's proportional. And y is what times x? It looks like should be 3/5. 3/5, 3/5, 3/5, yeah. So y is 3 over 5 times x, which is just that slope. Now is this proportionate? Let's see. We've got a change of 7 over 7, right? So it's actually 1. And then we've got a change of 7 over 7, which is 1 again. So we actually have a constant slope, but you can see that we can't, there's no multiplier. Yeah, it's a slope of 1, but it's not proportionate because that would mean that I should be able to multiply the x by 1 and get y or vice versa, and that's not the case. Remember we talked before about proportionate. Proportionate is where it has a constant slope, but it goes through the origin. And if we were to graph this line out, it clearly wouldn't. So this is not proportional. All right, cool. All right, this one's a little easier. We don't even need to do a slope. I can see that there's a common multiplier across, right? 2 times 4 is 8. 3 times 4, 5 times 4, so this is proportional. Y is 4 times x. What about this one? Well, y is what times x? This one would be 3 over 2, right? 3 over 2 times 4 is 6. 3 over 2 is 9. 1.5. So actually, yeah, it is proportional, and it's 3 over 2. Okay, y is what times x? Well, in this case, it's 1/4. In this case, it's 1/5. In this case, it's 1/6. So it's not proportionate. There's not a consistent multiplier. Here, it would be 2/5. Wait, no, sorry, 2/7. 2/7. 2/7. Yes, this works. Okay, my multiplier is, if I multiply 35 by 2/7, I get 10. 49 times 2/7, get 14. 2/7 times 63 is 18. So it's proportionate, and it's 2/7. All right, next, rewrite the following without an exponent. So guess what? If we have a fraction, and we're raising it to a -1, it's like both of these have a negative exponent, which means to turn them positive, they just kind of flip with each other. So it becomes 8 over 5, and that's it. This one is 7/4 to the negative 2. So I'm going to just flip the fraction, and then the exponent becomes positive, and then square both values, and I get 16/49. Next, we got 5/2 to the negative 3. So again, I'm going to flip the fraction to 2/5, make this positive cubed, and then cube both values. 2 cubed is 8, 5 cubed is 125. So it's 8. Three, to the negative 6 to the negative 5. Okay. Single positive exponent. We have an exponent to an exponent. This is introduction to the power rule of a power to the power of a power rule with negative exponent's whole number base. So when we have an exponent to an exponent, these guys interact by multiplying each other. So it's just negative 5 times negative 6, which is positive, positive 30, and that's it. Now we got 4 squared to the negative 8. Negative 8 times 2 is 4 to the negative 16, but we want to represent this with the positive exponent, so we throw it in the denominator, and it's 1/4 to the 16th. Next, we have 6 to the 5th to the negative 5. Multiply, we get 6 to the negative 25. And then we throw this under 1. And it becomes 1/6 to the 25th. Establishing facts about the interior angles of a triangle. Okay, it's saying that these lines are parallel. And we know that 1 is 96. We have 5 is 39. Okay. You see the 5 and 3 are both these, since these are parallel, right? This line here and L and K are parallel. 5 and 3 are what are called corresponding angles, which means they're equal, which means that 3 is also 39 degrees. So they're corresponding angles, and which means they're congruent or equal. So 3 equals 39. By the angle addition property, 5 plus 4 plus 1, 5 plus 4 plus 1 equals 180, because they're all along that straight line. Okay, and then angle 1 equals 96, angle 5 equals 39. Therefore, angle 4 must equal what? Well, let's try it. 39 plus 96 plus x equals 180. 39 plus 96 is 135. Subtract 135. X equals 45. So 2 and 4, let's see 2 and 4. 2 and 4 are what's called alternate interior angles. They're on the interior of these parallel lines, and they're on opposite sides of the transversal alternate side, so alternate interior. And that means they're congruent. Therefore, angle 2 is the same as angle 4. And we said angle 4 is 45 degrees. This is 45 degrees. Therefore, 1 plus 2 plus 3, 1 plus 2 plus 3, of course, equals 180, because they're all part of a triangle. So the relationship between angle 1, 2, and 3 is an example of the following rule. The sum of the interior angle measures of a triangle is 180 degrees. That's a super standard, important rule in geometry for all triangles. It's always the case. All right. Next. We got angle 5 is 46 degrees. Angle 4 is 37. And let's begin. 4 plus 1 plus 5 is 180, right? Because they're, again, all on a straight line, all around like that. Therefore, angle 1 must equal 37 plus 46 is 83. So 83 plus x equals 180. Subtract 83, and we get x equals 97. So 1 is 97. We see that 4 and 3 are alternate interior. So therefore 4 is 37. It's congruent. 3 must be 37. And we see that 2 and 5 are also alternate interior. So this is 46 and this is 37. Therefore 1 plus 2 plus 3 of course equals 180 and 180. Next, we got angle 4 is 52 degrees. Angle 1 is 80. All right. And now we're talking about angles 2 and 4. So these are our alternate interior angles, which means they're equal, which means that's also 52 degrees. Then we're talking about 1 and 5. 1 and 5 is this and this. Those are also congruent, but these are what's called corresponding. They're on the same side of the transversal. So these are corresponding angles, and they are congruent. Therefore, 5 equals 80. By angle addition, 5 plus 4 plus 3. 5 plus 4 plus 3 equal 180, because they're all in a straight line. And that means that this one is actually 48 degrees, right? 48 plus 52 is 100, plus 80 is 180. And therefore 1 plus 2 plus 3 is 180, which we know. We know the angles of a triangle add up to 180. Okay, I'm gonna log out and log back in to speed up ALEKS processing. Jose's chocolate bar is 38% cocoa. If the weight of the chocolate bar is 83 grams, how many grams of cocoa does it contain? Well, if 38% cocoa out of 83, we're doing 0.38 times 83. We can use the calculator here, so let's do that. So why am I doing 0.38? Because anytime we take a percentage, right, we take the percentage and we turn it into its decimal equivalent by moving the decimal twice to the left. We know that from DFP to go from percent to decimal, we go boom, boom. And then we take that decimal and multiply it by the total, and we get 31.54. Nearest tenth is 31.5. The chemist is using 387 milliliters of acid and water. 19.1% is acid. How many milliliters of acid are there? So 19.1% using DFP. We go once, twice from percentage to decimal. So once, twice. So it's 0.191 times the total. $73.9. Next we have 13.7% of this 138 pounds. So let's again go DFP, move it twice to 1.137 times 138. $18.9. Okay, let's keep going. Okay. Writing a rule to describe a reflection. So it's reflected across the x-axis. Now, let's see what's happening to A. So the bottom line is when we reflect across the y-axis, I'm going to kind of jump ahead to the rule. Look what's happening. The x values of each of the coordinates stays the same. What happens to the y values? The y values go from positive to negative, right? It's positive 5, it goes to negative 5. Positive 2 goes to negative 2. So all the x values are the same. Negative 6, 4, and negative 3. But what happens to these guys? The signs flip. So positive 5 goes to negative 5. Positive 7 goes to negative 7. Positive 2 goes to negative 2. Oh, wait. So the rule is the x stays the same and the y flips. Now we're talking about a flip across the y-axis. So look what's happening here. The y's stay the same, meaning the height of these guys or their vertical position stays the same, but the x flips. So all these y's have no change. But the x's all go, well, in this case, they all become positive. So the x's flip, the y's stay the same. And now it's rotating. Now this is interesting. We're flipping across the x-axis. Okay. I mean, it's not the x-axis. Y equals x, which is this invisible line that kind of goes like this. So this is a little different, but what's happening here? Well, let's look. The y value originally is 1, 5. Here it's 5, 1. So what's happening is the x's and the y's are like trading places. It's really, really bizarre, really interesting. But so check it out. So all the y's go to the x, so 2, 5, negative 2. And what about all those x's goes to the y's? So x was negative 8, now it's a y of negative 8. A y of 1 and a y of negative 4. And so it's like this. xy goes to yx. They trade places. Determine if figures are congruent and related by a sequence of transformations. So are they congruent? Yeah, they are. Congruent means equal. I'd say they are, right? They have a length here of 1, a length here of whatever this is, a little bit more than 2, a length here of 3, a length here of 2. They're both trapezoids, yes. So how could we go from A to B? So let's see which one makes it work. Translate figure A 6 units to the right. Let me copy this over here. So then translate it 6 units to the right. So we go 1, 2, 3, 4, 5, 6. Okay. Rotate that result counterclockwise 180 about the origin. So then it goes. No, 180 would put it here. So that's wrong. Translate figure down by 9 units. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9. So it comes down to here. And then reflect over the y-axis. No, that wouldn't give it. Reflect figure A over the y. Reflect figure A over the y-axis, so it would become here, and it'd be like this. Then translate the result down 9. No. Rotate figure A clockwise 90. So clockwise. So I think it would come down like this. So wait, it would like rotate across. I think it'd be something like this, right? If we do it clockwise. And then translate 7 units down. 1, 2, 3, 4, 5. Wait. Hold on, let's rotate. Oh, no, I'm sorry. It would rotate here. And I think that works. Then translate it down by 7 units. It should go to figure B. So this is the only one I think that makes sense. Let's see if that's right. Yeah. This is hard. Okay, next. Are figure A and figure B congruent? No, they're not. Look, this one has a bottom length of 4. This is a bottom length of 3. So they are not congruent. So none of these will get this to map over because they're not congruent. So it's none of these. Okay, so these ones are congruent, clearly, right? That you can see that they're the same shapes. So let's think about which one's going to translate over. I'm thinking something where it's a reflection across y, and then it goes down by 6. I'm just going to identify that's got to be the reflect over y. Yeah, this is definitely right. Translate figure A down by 6. Boom, move it down here, and then reflect over y. That will also work. Reflect figure A over the x-axis, which puts it here. Oops. And then rotate counterclockwise 180, which goes back up here. That won't work. Rotate figure 180. That would go here and then reflect across the y-axis. And that would go back here. So no, so only those two. Okay, constructing a Venn diagram to describe relationships between sets of rational numbers. So again, with our Venn diagrams, we're talking about universes, and the biggest one is it's the largest, the most inclusive. So rational numbers is the biggest group because it contains whole numbers and integers. Now, what about whole numbers and integers? Well, rational is kind of everything. It's fractions, it's decimals, positives, negatives. Integers are negatives, negative whole numbers, right, including 0, and positive whole numbers. So then it's the next biggest category because whole numbers is a subset of integers. It's just 0 and positive integers, 1, 2, 3, 4, 5, etc. So this is a slightly tighter universe, smaller universe, but it fits within the integer universe and also sits within rational numbers. So now let's find true or false. Some rational numbers are not integers. Yes, that's true because there's some rational numbers in this zone that are not integers. True. All rational numbers are whole numbers. That's not true. We have rational numbers out here that are not whole numbers, and here too. Negatives, fractions, etc. All whole numbers are integers. Yes, because whole numbers are completely within the integer universe, so every whole number is thereby an integer. All integers are rationals. Yes. All integers fall within the rational universe, so true. Set it up again. Some integers are not rational. Impossible. They're all rational. Some rationals are not whole numbers. That's true. Some integers are not whole numbers. That's true, like negatives. All rational numbers are integers. False. Fractions, decimals, those are not integers, and those are rational. All whole numbers are rational. Yes. All integers are whole numbers. False. Negatives that are integers are not whole numbers. Some integers are not rational. False. All integers are rational. Some whole numbers are not integers. False. All whole numbers are integers. All right, pie slice complete. Decimals are done. That's pretty cool. I think that's my second pie slice. The first one is whole numbers and integers. So I'm getting close to having to call it quits. Let me take another stretch break. Maybe we'll do a few more topics and then I'm going to call it a day. Decide whether or not it is a function. Now, identifying functions from relations. Here's the deal. What is a function and what is a relation? Well, these are all relations, okay? But whether or not they're a function has to do with the relationship between the domain and the range. Domain is x's, range is y's. The way you want to think about it is the x's can only be associated with one y. It's not the same with y's, right? Y's can be associated with multiple x's. That's fine, right? Like a six, like you see here with let's say the sky, right? We could have 6 be associated with sky and also 3 associated with sky. That's okay. But what we can't have is an x associated with 2 y's. What we say is x cannot cheat on y. Y can cheat on x, but x can't cheat on y. This x is cheating, right? It's matched up with rock and sun. So this is not a function. Now let's look at relation 2. Right here, boom. I got a b that's cheating. It's associated with a t and a c. That's no good. That c is also cheating. This is not a function. What about here? I see all unique x values, so I can already tell there's no x values cheating, so that is a function, right? If I saw another f associated with an 8, it would not be a function. I see an 8 associated with z and m, but the y's are allowed to cheat. That's fine. Boom, this one's cheating. -4 is linked up with a -8 and a -6. The x's are cheating, so it's not a function. All right, this looks good to me. 1 to 1, no x's are cheating. It's a function. No x's are cheating. It's a function. X's are cheating like crazy, right? Look at the 3. It's got a 9, a 3, and a -1. Not a function. -5 is cheating, right? Got a -3 and a 0. Not a function. Boom, boom, boom. This looks good. It's a function. No x's are cheating. No x's are cheating. No x's are cheating. This is a function. Ooh, 4 is cheating. -5. All of these are cheaters, right? They're all paired up with 2 values, so it's not a function. Introduction to the quotient rule with negative exponents, whole number base. Okay, we've got 9 to the -2 over 9 to the -6. So again, what I can do is I can kind of do it one of two ways. I'm gonna subtract down. That's the main thing. That's the main way to approach these divisions. So it's like -2 minus whatever's in the denominator minus -6. Minus a negative becomes a plus. So -2 plus 6 becomes 9 to the 4th. I could have also simply, when you have a negative in the denominator, I can move it up top. And I can move this down to the bottom. I can flip those when they're negative, and it becomes 9 to the 6 over 9 squared. Then subtract down, and it's 9 to the 4th. Same answer, 2 different methods. Okay, next we have 6 to the -3 over 6 to the 5th. So I'm going to subtract the bottom from the top, so -3 minus 5 is 6 to the -8. But we want to write this as a positive exponent, so we throw it under a 1, and that's it. Then we make that exponent positive, and we're good to go. Next we have 8 to the 4th, 8 to the negative 2. Subtract down, we have 4 minus negative 2, which becomes 8 to the, that's like a plus, right? Minus a negative is 4 plus 2, 8 to the 6th. All right, computing unit prices to find the better buy. A certain brand of coffee comes in 2 sizes. 11.3 ounce costs $2.88. 27.8 costs $6.48. Find the unit price. So we're talking about, check it out, price per ounce. Anytime we do per ounce or per something, it's, since we're doing price per ounce, we divide the price by the number of ounces. So in this one, it's 2.88 divided by 11.3. In this one, it is 6.48 divided by 27.8. So let's do the division here. And it's 0.25, right? We're rounding to the nearest hundred. So this is 25 cents. And this one is 6.48 divided by 27.8. which equals 23 cents. So that's 23 cents per ounce. So this is 0.25, this is 0.23. So which one's the better buy? Well, check it out, this is cheaper, right? So the 27.8 ounce is cheaper, and that's that. So I'm gonna skip all this, right? We're just going straight to cost per pencil, or for each pencil. So we take the total cost of brand A, it's $4.48 divided by 24. The second one is $6.24 divided by 36. And let's calculate these. Okay, 0.19, and then we have 6.24 divided by 36 equals 0.17. All right, so brand A is 0.19 and brand B is 0.17. So which one is better? Brand B. Okay, now we're doing price per kilogram. So same thing, we're dividing by the number of kilograms. Anything that's after the per, we're dividing by. So 12.98 divided by 6.35 for that first one. This one is 14.88 divided by 7.03. $2.04 here, and then this one is 14.88 divided by 7.03, which is 2.12. All right, there we go. That's our price per kilogram. So 2.04 and 2.12. So which one's a better buy? This one's cheaper, right? So the 6.35 is a better buy. Okay, certain medicine is given an amount proportional to a patient's body weight. Suppose a patient weighing 104 pounds requires 103 milligrams. Wait, word problem and proportions problem type 1. Oops. Okay, certain medicine is given in an amount proportional to a patient's body weight. Suppose the patient weighs 104, requires 130 milligrams. So somebody weighing 104 pounds requires 130 milligrams. That's the proportion. So remember, we've got weight over milligrams of medicine. What is the weight, meaning we're solving for the weight on this side of somebody who requires 278.75. And you see in this proportion, you see I'm setting up the weight on top, milligrams on bottom, and now we do cross multiply and solve for x. So this is 130x equals 104 times 278.75, which is 28990. And then we divide both sides by 130. And we get 223. All right, excellent. Next, we've got Latoya runs 6 miles. So I'm going to put miles up top in 45 minutes. So this is minutes on the bottom. At the same rate, how many minutes would it take to run 4 miles? And we're solving for x. Now let's cross multiply. That's 180 equals 6x. Divide both sides by 6. And we get x equals 30 minutes. Last but not least, there's a sales tax. So tax of $16 on cost of $232. And the sales tax on the second item is $22. How much did the second one cost? That's what we're solving for. Cross multiply. 22 times 232. 5104 equals 16x. We divide both sides by 16. And we get x equals 16 equals 319. Okay, guys, that is a 2-hour plus live stream. I think I'm going to have to call it in for today. Let's take a look and see how far we got. So 77%, that's pretty good. 23% left. Getting really close to finishing this pie. So I'm going to take these videos, edit them down, chop them up, get them integrated into my course, and then just plow away. Hopefully again tomorrow I'll do another nice long live stream. And we'll get there pretty soon. Hopefully by next week, this course should be finished and pending approval from Udemy. Again, if you like what you see and want to see more, make sure to click that subscribe button. If you like this video, click that like button. If you have any questions on the material that I covered or anything that you want to see in the future, make sure to leave a comment in the comment section. And so the villain, or I don't know if you're still watching. Oh yeah, okay, so Sam Fam, if you're watching right now, I'm doing a live SAT section of math tomorrow. Every Wednesday is when I do those 5 problems, but next week is going to be a really intense training session. So because the following weekend we're going to have the SAT. I assume you're taking it then. So I'm going to be doing a live stream every day next week, Monday through Friday, to get everybody as prepped as possible for the upcoming SAT. So definitely tune in for that. And hopefully that will be helpful. You'll be able to ask questions and so on those live streams. So that's it for today. Thank you guys so much for joining. Just to answer this question from the villain, do I ever forget a formula? Yes, I suppose. I mean, there's not really, I guess on the SAT stuff, I guess I don't forget any formulas there. And the only really tricky formulas, if I do forget them, they're provided on the front page of the SAT. But I mean, I've been practicing this stuff a lot for the last 5 years, so I don't really forget the formulas so much anymore. But there are always alternative strategies in solving problems. So even if you forget a formula, I think it's important. That's why I try and teach the explanation and have a broader understanding of each concept. And I mean, when you do, you can usually find workarounds in case you forget a formula. The best example of that is distance formula. It's a cumbersome formula, but if you understand that it's grounded in the Pythagorean Theorem, which is much easier to remember, you can usually find the distance of 2 points by quickly making a crude drawing and then applying Pythagorean Theorem. So stuff like that. In terms of what subject do I hate the most, I hate to admit this, but I don't like lengthy word problems. Lengthy word problems are just, I don't know what it is, but they're boring to me. To me, it's like you're trying to extract the math, which is the fun part. And then once you get the math out, then it's kind of fun. So that's the part that I find boring and my brain shuts down. But I've had to get more comfortable with that because the SAT has now switched over to having more and more words in the math section, more word problems, etc. So it's just goes hand in hand with understanding and being an expert of that test. All right, thank you guys so much for joining. Again, I'll see you guys tomorrow. Probably do another ALEKS live stream, but more importantly, I'm going to do an SAT live stream. So until then, take it easy and have a great rest of your day.